In this video here, we're going to take a look at finding areas. So we can use the vector product to easily solve problems involving areas of triangles and parallelograms. So let's just start then by looking at finding the area of triangles by using the vector product. So to get us started here then, let's just have a look at finding the area of triangles by using the vector product. So let's say then that we have a triangle OAB where O is the origin, A is the point with position vector A, and B is the point with position vector B. So if we draw that here then, we get something like the following. Now, if we want to find the area of the triangle OAB, we can easily do that by using this result here. So we're going to use a half AB sine C. So if we do that then, what we get here is a half times by OA times by OB sine of beta. So this here then is just the same as a half times by the magnitude of the vector A times by the magnitude of the vector B times by sine of beta. And then based on the definition here of the vector product, this is simply a half times by the magnitude of A cross B here. Now you should also be aware that we can obtain this result here by using the fact that the magnitude of the cross product of the vectors A and B gives the area of the parallelogram. Well, given that we have a triangle here, right, we just divide that by 2. So let me try quickly add this to my diagram here. Let's do it in dark red. If I draw the parallelogram here, it's probably not going to be perfect, but you'll get the idea. Something like the following here, right? So as we can see then, we have our parallelogram here. So the area of this full parallelogram here, so the area here then of this parallelogram, this is the same as the magnitude of A cross B here. Okay, so the vector A crossed with the vector B. Now, given that this is a parallelogram here, but we have a triangle, right? Let me quickly do this in green. So we have this triangle here, right? We've got this triangle here, like so. Well, clearly then, these two triangles here are congruent. So we just divide this by 2, right? So the area then of the green triangle is a half times by the magnitude of A crossed with B. Okay, so just the same here then as what we've got. Now the previous example was for a triangle with a vertex at the origin. And this won't always be the case, and so we need a formula to allow us to find the area of any triangle by using the vector product. So let's say then that we have the triangle ABC here, where the position vectors of the vertices A, B, and C are given as A, B, and C respectively. So if we draw the triangle here then, we get something like the following. So if we want to find the area of the triangle ABC, this would be given as follows. So the area of ABC is simply equal to a half times the magnitude of the vector AB cross the vector AC here. So we cross these two vectors, take the magnitude, and we times it by a half. Okay, so very similar to what we introduced on the previous page. Now based on this definition here then, we could simply write this also as a half times by the magnitude of B minus A crossed with C minus A, right? This is just the vector AB. This here is just the vector AC. And in that case, then we could also write this here as a half times by the magnitude of A cross B plus B cross C plus C crossed with A. Okay. Now it's unlikely that you'll need to use either of these two lines here. Generally speaking, you need these more for kind of like proof type questions, but it is useful to be aware of this fact here. Okay. So that's everything that we need then for finding the area of triangles by using the vector product. So to finish with here then, let's just have a look at finding the area of parallelograms by using the vector product. So let's say that we have a parallelogram where A and B have position vectors of A and B respectively. So if we draw that here then, we get something like the following. Now we should be aware here that the area of the parallelogram OABC is simply the magnitude of this cross product here, right? So I did mention this on the previous page when we had the triangle, and I kind of extended that to be a parallelogram, that the area then of the parallelogram OABC is simply the magnitude of the vector A crossed with the vector B. Okay. So let's say then that we have a parallelogram where A, B, C, and D have position vectors of A, B, C, and D respectively. Then in that case here, the area of the parallelogram ABCD is equal to the magnitude of the vector AB crossed with the vector AD here. And this is the same as the magnitude of B minus A crossed with D minus A. So this is just AB here. This is just AD. And now by expanding this here and just using the properties then of the cross product here, this is just the same as a half times by the magnitude then. So we've got A cross B plus B cross D plus D cross A here. So again, it's unlikely for kind of a typical A-Level Further Maths FP1 question that you're going to need to use either of these two lines here. But again, it's just worth being aware of. Okay. So there we have it in terms of an introduction here to finding areas. The best way to kind of work through this here is just run through a couple of practice questions. So let's get started then with question 1. So to get us started here then, let's just begin with question 1. So as we can see here for question 1, we're told that the vertices of a triangle are given as follows. So A has coordinates of 2, 1, minus 1. B has coordinates of 1, 0, 4. And C has coordinates of 3, minus 1, and 1. So for the first part of this question here, part A, all we want to do is find the cross product of these two vectors, AB and AC. So obviously a good starting point for this question, right, would be to actually find these two vectors, AB and AC. So starting off then with part A here. So for the vector AB, and what I'm going to do here is give each vector in column vector notation. So for the vector AB here, that would simply be B minus A. So I get 1 minus 2. That would give us minus 1. We then get 0 minus 1 here. So again, we get minus 1. And then finally, we have 4 minus 1, which is just the same as 4 plus 1. So we get 5 there. We also need the vector AC here as well. So for the vector AC then, again, given this as a column vector. So what do we get here? So for AC, we do C minus A. So I get 3 minus 2, which is 1. We then do minus 1 minus 1. So I get minus 2 there. And then finally, 1 minus 1, just the same as 1 plus 1, giving us 2 there. Okay. So now for the cross product here then of these two vectors. So therefore, the cross product here of these two vectors, so AB cross with the vector AC, using the determinant form here then. So this would be the determinant here of a 3x3 matrix. Along the top row, we have the unit vectors of I, J, and K here, like so. Along the middle row, we have this vector AB. So I get minus 1, and 5. And then along the bottom row here, we get 1, minus 2, and 2. So 1, minus 2, and 2. Okay. So what I need to do here is find the determinant then of this 3x3 matrix. And the way that I'm going to do this here is to expand along the top row. So what I'm going to get here then is I times by the determinant here then of the 2x2 matrix left over once we delete this row and this column. So I get minus 1, 5, minus 2, and 2. So minus 1, 5, minus 2, and 2 there. Like so. We then get minus j. Don't forget it goes plus, minus, so on and so on. So it's plus, minus here. So I get minus j. We then get the determinant here of the 2x2 matrix left over once we delete this row and this column. So we get minus 1, 5, 1, and 2 here. So minus 1, 5, 1, and 2. And then finally here, we get plus k. So plus k times by the determinant then of the 2x2 matrix left over once we delete this row and this column. So get minus 1, 1, and minus 2. But this should all hopefully be pretty straightforward, right? This is just basic core pure here, right? Find the determinant of a 3x3 matrix. So get minus 1, 1, and minus 2 here. Okay. So let's evaluate then each individual 2x2 matrix here and the determinant of that. So we've got minus 1 times by 2, so that's minus 2. minus, so I've got minus 2 times by 5. So in other words, I've got minus 2 here plus 10. That would give me 8 there. So I times by 8, we get 8i, like so. I then got minus j times by this determinant here. So I get minus 1 times by 2, so that's minus 2. We then subtract 5 here, so I get minus 7. So minus j times by minus 7, that gives me plus 7j here. So plus 7j there. And then finally here we have k times by this determinant here. So minus 1 times minus 2, so that's positive 2. We then get minus 1 here. So in other words, 2 plus 1 giving us 3. So we get 3k there. Okay, like so. And there we have it. So this here then is AB. It's the vector AB crossed with the vector AC. Okay, and there we have it. So that gives us the solution there to part A. And now moving on to the very last part here, then part B, it says, hence find the exact area of the triangle ABC. So this question is structured in such a way that it kind of helps you get to the answer here then for part B, right? It helps us to get the exact area of the triangle ABC. And the reason for that is because the area then of this triangle ABC here, so the area of ABC would be given as a half times by the magnitude then of AB crossed with AC, right? So AB crossed with AC here. Well, we've already evaluated, right? AB crossed with AC. So all I need to do here is find the magnitude of this vector here and then times it by a half. So what I'm going to get here is a half times by the magnitude here then. So this is the square root of 8 squared plus 7 squared plus 3 squared. So we get 8 squared here plus 7 squared plus 3 squared. So if we evaluate this here then, what I get is a half times by the square root then. So I get 64. I've got 64 plus 49 plus 9. And then if we simplify this here, what I get then is a half times by the square root of 122 here. Okay, feel free to just use your calculator, right, to evaluate this. You don't have to do it off the top of your head. So we get a half times by the square root of 122 here, and this is the exact area of the triangle ABC. So area of ABC here. And there we have it. So that gives us the solution there to question 1. So moving on to the very last question here, then question 2, as we can see, we're told that the vertices of AB and D of a parallelogram ABCD are given as 1, 0, 2, 2, minus 1, 1, and 5, 1, 0 respectively. The question then asks us to find the exact area of the parallelogram ABCD. So for a parallelogram here, we should be aware that the area, let's just write this down here to begin with, the area here is equal to the magnitude of the vector AB crossed with the vector AD here. Okay, so let's just start then by finding these two vectors of AB and AD. So the vector AB here, so this is equal to, so we do B minus A here, so I get 2 minus 1, so that's 1. Right, this is a column vector here, so I get 1. I then do minus 1, subtract 0, so I just get minus 1 again. And then I do 1 minus 2 here, so again, I get minus 1, like so. So this here then is the vector AB. We do also need the vector AD here. So for the vector AD then, again, if I represent this here in column vector form, so D here is 5, 1, 0, so I do D minus A. So 5 minus 1 is 4. We then do 1 minus 0, so I get 1 there. And then finally 0 minus 2, giving us minus 2. Okay, so now what we need to do here is find the cross product then of these two vectors here, AB and AD. So let's do that over here. So for AB, cross with AD, I'm going to use the determinant form here to find this, right? So this is the determinant then of a 3x3 matrix. Along the top row, we have the unit vectors of I, J, and K, like so. So along the middle row here then, I'm going to have AB, so that's 1, -1, and -1, like so. And then along the bottom row here, we have the vector AD. So I get 4, 1, and -2. So 4, 1, and -2 there. Okay. So finding the determinant here then, I'm going to expand along the top row here. I think that's the easiest way to do this. So what would I get here? So I'm going to get positive I. Then we times this here by the determinant then of the 2x2 matrix that's left once we delete this row here and this column. So I get -1, -1, 1, and -2 here. So -1, -1, 1, and -2. We would then get -j here. So it goes plus, minus, minus, so on and so on. But obviously we're only going along the top row here. So -j. Then we times this here by the determinant of the 2x2 matrix left over once we delete this row here and this column. So I get 1, -1, 4, and -2. 1, -1, 4, and -2. And then finally here we get plus k. So plus k times by the determinant then of the 2x2 matrix that's left over once we delete this row here and this column. So I get 1, -1, 4, and 1. 4 and 1 there, like so. So clearly what we need to do here then is evaluate each of these 2x2 determinants. So I get I times by, so what do I get here? I get -1 times -2, so that's 2, minus -1, so in other words I get 3 there. That would be 3i. So let me just erase that. Let's write it down again, just to save a little bit of time. So we get 3i there, like so. We then have -j. So for this determinant here, I get 1 times -2, so that's -2 minus -4. So -2 plus 4, that gives me 2, times it by -j, I get -2j, like so. And then finally for k here, so I do 1 times by 1, which is 1, minus -4, so I get 1 plus 4 there, so that's 5. So we get 5k there. Okay, so what I need here then is the magnitude here of this vector, and then I don't need to times it by half, right, because we have a parallelogram. My first instinct is to always times 3 by half. Obviously, we don't need to do that because we have a parallelogram as opposed to a triangle. So all I need to do here then is find the magnitude of this vector here. So therefore, the area is equal to the magnitude here of this vector. So I get 3 squared plus -2 squared, and then finally plus 5 squared here. So what would this give us here? I'm going to get 9 plus 4 plus 25. I get 9 plus 4 plus 25, like so. Well, in that case, I'm going to get 13 plus 25, so that's the square root of 38 here. Obviously, we can't really simplify that, right? I can't simplify that third here. So there we have it, right? So the area here then, the exact area of the parallelogram ABCD is equal to the square root of 38. And there we have it. So that gives us the solution there to the very last question, question 2. And that actually brings us to the end then of this video here on finding areas.